Hello and welcome to this video. Today we are going to, without a calculator, use some algebra techniques and calculus techniques to analyze the graph of functions. In order to do that, we're going to first determine our domain and range of the function that we are given. Keeping in mind that if we have a real-world application, we need to consider the context and take out any values from the domain that might not be feasible. For instance, you can't have negative feet, that kind of thing. Second, we're going to determine the intercepts. We know how to do that. X-intercept, put a y in for 0 and solve. Y-intercept, put a 0 in for x and solve. So we're going to determine the intercepts and the asymptotes. These are all algebraic techniques that we've done in previous algebra classes. Then we're going to locate the x values of our first derivative and second derivative. See where they are 0 or undefined. You'll recall critical values, critical numbers. Use those results to find the relative extrema, and points of inflection. Now, we're going to use everything that we've done in the previous sections, the previous lessons. We're putting it all together here, and we're going to make that connection to the graph. Now, for time purposes, we've got the graph of f of x equals x cubed plus 3x squared minus 9x plus 5. I'm going to make myself a note here. You can find zeros, factors, by using synthetic division. So synthetic division, what you do is you take factors of the constant, so plus or minus 1, plus or minus 5, over factors of the leading coefficient, plus or minus 1, and you would try those into synthetic division to see where your remainder is 0. And that helps you factor. So you'd be using synthetic division along with the factor theorem to find the factors of this function. And what you would find is that 1 would have a multiplicity of 2, and that negative 5 is also a factor. Not a factor, a root. X plus 5 is the factor. Negative 5 would have been a root, a solution, or a 0. Those are all synonymous. So our intercepts, we're going to put a 0 in for y. When we put a 0 in for y, we're going to get an intercept of negative 5, 0. We'll get an intercept of 1, 0. And when we put a 0 in for x, we get an intercept of 0, 5. So our y-intercept is 5, 2 x-intercepts, 1 at negative 5, 1 at 1, 0. Now what makes the 1 at 1, 0 special is it's a multiplicity. And it's a multiplicity of 2, meaning that the graph is going to bounce off that x-intercept and it's not going to go through the x-intercept. Asymptotes, there are no asymptotes for this function because it's a polynomial function. So there are no asymptotes. In fact, the domain of this function is all real numbers, and the range of this function is all real numbers. So we denote that by saying negative infinity to positive infinity. Now, where might this graph be increasing and or decreasing? We're going to come over here and we're going to find the first derivative. So I'm going to say f prime of x. I'm going to move this over here. I love it that I can do that, and when I'm on paper and pencil I can't do it, but when you're dealing with technology there's so much that you can do. So our first derivative, I'm going to go back to the original form, the standard form of our function, and I'm going to find that first derivative is 3x squared plus 6x minus 9, which factors to be 3, and then that would leave me x squared plus 2x minus 3, which factors to be x plus 3, x minus 1. If I set that equal to 0, I'm going to be able to find some values there that I'll be able to put on a number line. So I set that equal to 0, and I get negative 3, and I get positive 1. Now if I take negative 10, that happens to be in the interval from negative infinity to negative 3, and I put it back into the first derivative, I will end up with a positive output. If I put a 0 in, I will end up with a negative output for the first derivative. And if I put a positive 2 in, I'll end up with a positive output for that interval. Now let's find our second derivative. So I'm going to change the color here. Our second derivative, I'm going to go back to this form of our first derivative, and our second derivative is 6x plus 6. When I set that equal to 0, x equals negative 1. So we're going to draw our number line, and we're comparing this now, or we're testing this into our second derivative. So I have negative 1 here. When I put in a negative 10, I'm going to end up with a negative output. And when I put in a 0, I end up with a positive output. So let's now work our way backwards. Positive output for the second derivative is concave up. Negative in that second derivative is concave down. I already started to write down, which makes me want to go back here and fix my arrow. There we go. Concave up, concave down. Now, what did it mean for our first derivative? So for our first derivative, to have this positive, negative, positive. Well, positive was increasing, negative was the interval in which we were decreasing, and then the positive, once again, is the interval in which the function is increasing. So we've got our first derivative, our second derivative. Now, one more thing to do. This value right here helps us find our point of inflection. So when I put a negative 1 back into the original function, a negative 1 back into the original function, f, I'm going to get a 16 out. So negative 1 cubed plus 3 times negative 1 squared plus 9 plus 5, that is where we're getting our 16 from. So we're increasing from negative infinity to negative 3, and then again from 1 to infinity. Our graph is decreasing from negative 3 to 1. Our extrema, that's going to come from this value right here. Let's make this purple. So increasing to decreasing is a max. Decreasing to increasing is a min. So our extrema, we're going to have a relative max at negative 3 something or other, and then we're going to have a relative min at 1 something. So f of negative 3, when we put that negative 3 into the original function, I'm going to get 27 plus 27, actually negative 27 because it's a negative 3. Negative 27 plus 27 plus 27 plus 5. So that's going to be a 32. And when we put a 1 in, a positive 1 in, we get 1 plus 3 minus 9 plus 5, which is 0. And then our concavity was this color. So concavity, we've got from negative infinity to negative 1, concave down, and then from 1 to infinity, concave up. And then in red, our point of inflection is negative 1, comma 16. So this is fantastic. We're going to take this and we are going to graph this guy. So I'm going to go on to another page. And I'm going to create my graph here. There we go, something like that. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then I'm just going to say 2, 4, 6, 8, 10, 12. So that would be the same, 2, 4, 6, negative 2, negative 4, negative 6. And I think I'm ready. So we've got some intercepts. Let's do this in blue. We've got some intercepts at negative 5, comma 0, 1, comma 0, and then a y-intercept at 0, 5. No asymptotes. We're increasing from negative infinity to 3. Sorry, negative infinity to negative 3. Is that correct? Let's look. Negative infinity to negative 3. Can I just do this? I can. I appreciate your approval, though. I do. That multiplicity of 2 is going to come in handy. I'm going to copy this, and I'm going to paste it. Let's keep it right there. Excellent. So we've got our intercepts, negative 5, 0, 1, 0, and 0, 5. No asymptotes. We're increasing from negative infinity to negative 3, and then again from 1 to infinity. Decreasing in between there. We've got extrema at negative 3, negative 32. Let's do that one next. Negative 3, 32. I think I said negative 32, but it's negative 3, 32. So that's going to be way, 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 way up here. So I'm just going to do this. There's no way that I can put it up there. I mean, I don't have room. So I'm just going to say negative 3, 32. I'm going to pretend that that's where it is. So our graph is going to be increasing, right? Increasing until it gets to this relative maximum. And that is going to happen at negative 3, 32. And then from negative 3 on the x-axis to positive 1, our graph is decreasing. So that's where it turns and it's decreasing. Okay. Now, what's happening at 1? Well, what's happening at 1, because it was a multiplicity of 2, is it's touching it and bouncing off and going back up. Now, let's look at this concavity. Okay. Let's look at the concavity, because here it doesn't seem like we really need to worry about that concavity, but it is important. Negative 1, 16. Oy. We're going to have to pretend that negative 1, 16, because we couldn't go all the way up to negative 32. So we're going to have to pretend that negative 1, 16 is right about here. So that's where that concavity changed. So it's hard to see right here what's happening, but we're concave down, and then we're going to turn and go concave up. So if you were to zoom in here, that's what would be happening. It's actually a pretty cool thing. And I've got some other graphs. Don't you worry. I've got some other graphs that you will be able to see pretty cool like, most especially in this next example. This one, I'm not going to lie, is pretty cool. And I hope that I can reproduce the coolness in the graph that this one has in the next video.